Okay, the third unit we covered was states of matter. It covered the difference between solid, liquid, gas, and each of their characteristics, as well as state changes. Okay, so we're filling in the boxes with yes or no. Solids, do they have a definite shape? Definite means not changing. So do solids have a not changing shape? You would say yes. Do solids have a definite volume? Yes, because you can measure it. Do liquids have a definite shape? No, because it can change depending on their container. Do liquids have a definite volume? Yes, because you can measure it using a graduated cylinder, a beaker. Do gases have a definite shape? No, because their shape is constantly changing based on the container that they're in. Do gases have a definite volume? No, because they spread out to take up as much space as they can. Label each picture according to its state of matter. The first one would be a solid, the second is a liquid, and the third is a gas. All of these pictures are showing solids because the two types of solids are amorphous and crystalline. Amorphous means there is no pattern, which is why the first one is amorphous. There is no pattern between the green and the gray atoms. The second one is also amorphous. That's melting glass. There's no pattern that you can find in that picture. The third one is crystalline. There's a pattern between the green atoms and the gray atoms. The one on the very bottom right is also crystalline because it's showing the real life image underneath an electron scanning microscope of the representation of the green and gray model above it. And the last one is also crystalline because you have a pattern of hexagons. Okay, what characteristic of liquids is shown in each picture? So this is showing surface tension. This is an attraction between particles at the top of a liquid. This characteristic of liquid is viscosity. And viscosity is the resistance of a liquid to flow, meaning to move. So which one has the highest viscosity according to this graph? Highest viscosity means it should be going the slowest, which should be C. The lowest viscosity would be A because it is going the fastest. Highest flow would also be A. It's going the fastest. Lowest flow is C. It's going the slowest. The strongest attraction being which ones are holding on to each other the tightest, which ones are going the slowest because they're not letting go, and that would be C. The weakest attraction would be A. Highest viscosity should be the liquid that's flowing the slowest, that would be D. Lowest viscosity is A. Highest flow A. Lowest flow D. Strongest attraction D. Weakest attraction A. What is temperature? Temperature is just a measure of how fast particles are moving. So if something is hot, particles are moving very fast. If it's cold, particles are moving slower. And pressure is something we talked about when we talked about gases. Pressure is the number of times are like bumping into each other or hitting the outside container. So a synonym for pressure would be a force that's pressing on the outside. And your easy way to remember that is pressure sounds like press. It's got that word inside. That's its root word. Volume is just how much space an object takes up. That was covered in our last unit. It can be measured in centimeters cubed, meters cubed, or milliliters or liters. List the states of matter from the least amount of energy to the most amount of energy. The slowest would be solid, and the next fastest is liquid and gas. Okay, what is the volume when pressure is 50 kPa? So you're going to look at your graph, we're going to find at 50 kPa the volume is 6. What is the pressure when the volume is 8? When the volume is 8, it should be around 35 or 40. From 6 to 2 liters, what happens to pressure? So what I like to do on these problems is look at the actual numbers themselves and then figure out, are the numbers increasing or decreasing? So at 6 liters, you are at 50 kPa, and at 2 liters, you'd be at 150 kPa. So you went from 50 all the way to 150. Which is an increase. From 150 to 300 kPa, let's go back here and look at those numbers again. At 150 kPa, the volume is 2. And at 300 kPa, the volume is only 1. So if you go from 2 to 1, the number is getting smaller. So you're going from 2 liters to 1 liter, which is a decrease. So your way to tell if this is inverse or direct, you can do this 2 ways. The first one I would do is to look at your graph. Is it going up or is it going down? If it's going down, that tells you it is an inverse, meaning opposite. Your other way to know is by looking at your questions that you answered. The first one I said from 6 to 2 liters. From 6 to 2 is a decrease, but when you answered what happened to pressure, your number increased. So one decreased, one increased. It also tells you that it's opposite. And the other gas law we looked at was Charles' law. Charles' law is looking at temperature and volume. So it says temperature rises from 0 to 100 degrees Kelvin. What happens to volume? So we're going to do the same thing. At 0 degrees Kelvin, at 0 degrees for temperature, the volume is about 2, and at 100 the volume is about 3. So if you go from 1 to 3, that increases. So your volume went from 1 liter to 3 liters, which is an increase. The next one, we're looking at temperature decreasing from negative 100 to negative 200. So at negative 100, the volume should be about 1.5, and at negative 200, it's about 0.6. So you went from 1.5 to 0.6. So your number is getting smaller. That is a decrease. Okay, the next part we're looking at is state changes. From a solid to a liquid is melting. And our example for that could be like ice to water. The way you know if it's endo or exothermic, you would think is, would the atoms be speeding up or slowing down? If you go from solid to liquid, your particles are speeding up, energy goes in, it's endothermic. Temperature is going to go up, particle speed is going to go up. Liquid to a solid is freezing. So the opposite of melting would be water to ice. And if you go from water to ice, the energy is leaving because water is moving fairly quickly. Its atoms are moving around. As it becomes an ice, the particles only vibrate in place. So energy left, it's going to get colder, which is why the temperature goes down. Particle speed also goes down. Liquid to a gas is evaporation. That'd be going from like water to a cloud or to water vapor. In order for water to form a gas, you're going to need to put some energy in, like boiling water. You can actually see the steam come out. That's energy going in for endothermic. When you boil water, you'd have to increase the temperature, so it's going to go up. And the particle speeds will actually speed up. You can see that if you boil water, you can see the bubbles kind of moving around. Gas to a liquid is the opposite of evaporation, that's condensation. So that'd be like raining, going from a cloud back to water, back to rain. Normally when it rains, it is actually getting colder outside, meaning energy is taken out. It's exothermic. Temperature is going down. Particle speed is going down. Solid to a gas would be sublimation. So a good example of that was dry ice. So that'd be ice to a gas, where you could actually see the gas coming off of the carbon dioxide. If you're going from ice to a gas, you're warming things up, you're putting energy in, that's endothermic, your temperature goes up, particle speed goes up. Gas to a solid is the opposite of sublimation, which is deposition, like you're depositing solids. So you'd be going from a gas to ice. You're cooling it down, so it's exothermic, temperature goes down, particle speed goes down. And that's just a graph to help you visualize what we did on the last page in that chart. And that's the end of our states of matter unit.